Geology, and recording is in progress. There's no test at the end of this, but please feel free, any questions you have, to bring them up as Dee mentioned, and we will address. So my name is Greg Berman. I'm with the Sea Grant program, which is a NOAA program at 34 different institutions across the country. Our program is based at Woods Hole Oceanographic Institution, and the other half of me is the Cooperative Extension at Barnstable County. So typically I provide technical assistance to towns, to homeowners association groups, things like that, when they have questions about shoreline stabilization projects, about sea level rise, about vulnerability. So I can provide technical assistance in that manner. And we also, host conferences, do workshops, presentations like this. So we'll get right into it. If we can advance. Okay, it's just going a little slow. Okay, there we go. We have advanced. So I've planned the talk for about 45 minutes, give or take, depending if we get many questions along the way, and we can address those at the end also. So we can't really talk about Cape Cod unless we go back to glacial history. That's really where most of Cape Cod came from other parts and got deposited here. Some of the specific features we'll be talking about are kettle ponds, the mudflats, the flats of Brewster, some glacial erratics, really just how Brewster has changed over time. And this is kind of geared towards geology, as the title might have, clued you in on. I had given a talk to this group earlier that had more to do with like sediment transport along the shoreline. So there might be like one or two slides that'll be a little bit of a refresher, but this should hopefully be mostly new material. So we're talking about glacial history, right? We're talking mostly about the last glacier that came through, because usually the last glacier wipes all evidence of previous glaciers out of the way. So the last one was here about 25,000 years ago. That was the Laurentide ice sheet, named from that portion of Canada where it's originated and moved south. So 25,000 years ago, it reached its maximum. I'm going to try to, oh, that wasn't good. Let's see. There we go. I'm going to try to take my mouse, and Dee, can you just give me a thumbs up? Can you see the arrow of my mouse? Okay, cool. So here we are 25,000 years ago, last glacial maximum. And this gray graph here is sea level over time for thousands of years ago. So we had another glacial maximum about 150,000 years ago. Sea level has been higher than it presently is. It's been much lower than it presently is. Changes over time. Nothing new there. So we're going to talk about this ice sheet. It melted fairly rapidly and then, slowed down considerably in our, human history. But during this rapid melting phase, we had a lot of water added to the ocean. So as it retreated about 15,000 years ago, the ice on Cape Cod was gone. It had melted, the water had worked its way back into the ocean. That doesn't necessarily mean that, the entire ice sheet had melted, just in our particular region, right? So there's still plenty of ice up in Maine, up in Canada, taking up and still continuing a relatively rapid melt and adding water to the system. So down here in the lower left-hand corner, about 11,000 years ago, this green area, you can imagine that is all land mass. Blue is water, makes sense. But you could have walked from Cape Cod all the way out to George's Bank, right? So this was exposed, no fishing out in George's Bank yet. The ice sheet continued to melt, water was going into the oceans, and now 6,000 years ago, George's Bank is finally underwater. You still could have walked out to the islands, no ferries needed, but now we're getting waves and erosion, storm impacts across the Atlantic, not just this local area, right? So this is when erosion really started taking off, especially for the outer arm of Cape Cod and how exposed it is. Eventually, we get to our present day configuration, but we're going to kind of dive in a little more granular versus these, 5 to 10,000 year jumps to see what was happening during these time stages. And the evidence of, what this looked like is all in the superficial geology of Cape Cod. So in that upper left-hand corner, you may or may not be able to read it, but for some reason we've shifted all the ice is green. So all that was ice. That was the last glacial maximum about 25,000 years ago. So that glacial maximum was right on the islands, right? And as this glacier moved to the south, it reached its southern point. It couldn't go any further because that's where it started to melt. And as this ice sheet moved from the north to the south, think of it like a very slow moving river, it picked up things along the way, pretty much everything. It would get boulders, gravel, sand, mud, clay, everything in between. And when it reached, its melt edge, terminal edge, everything dropped out. Now, the smaller stuff, like the sand and gravel, could get moved by the rivers. The bigger stuff, boulders, large cobbles, that's not getting moved as easily. So those melt edges deposited something called a terminal moraine. And these are the big stuff that got dropped out. There's not too much of that in the Brewster area. You can kind of see, we'll talk about this one first. So here we are on the vineyard, and you can see large terminal rain deposits. This is because the big stuff got dropped out there, and then material kind of filled out from there, creating these floodplain materials. Now, from 25,000 years ago, it melted rapidly and then kind of stalled out. Right. So that was one terminal. Here's another terminal face. So right along the Cape Cod shoreline, that's really why these Elizabeth Islands are in this configuration. It was a lobe of ice along here, and that's why they're, so rocky. That's how they have survived the erosive forces, much rockier than some of these sandy materials down there. Kind of going all the way into the upper Cape and kind of petering out kind of mid-Cape-ish, really before we get to Brewster. So Brewster, you don't really have those terminal moraine deposits out here. It's mostly outwash deposits, so floodplain material. And now we'll kind of show what that would look like. So here we have our receding glacier. It's melting. It's, not just bringing sand and gravel. It's also bringing a large volume of frozen water. And when that water melts, it then can form floodplains and distribute that material along a floodplain. Various glacial features that we'll be talking about. Came and Kettle topography. I'll have some images kind of showing a little bit more what that is. Drumlins and eskers have to do with how material is transported underneath the glacier. And then that terminal moraine we talked about, the kind of phase one out at the islands. And then when it stalled out, it formed another terminal moraine out here. So when we're talking about these glacial lobes, it was one ice sheet, but there's different lobes, and that kind of moved independently, right? So you can think of the terminal moraines along here, right there, forming those terminal moraines. But we also had edge moraines, kind of in between these lobes where a lot of material would get dropped out. Now, 20,000 years ago, you can see all three lobes extending fairly far south, certainly down to the islands, that maximum extent. And now we're thinking about this middle area about 18,000 years ago. We're starting to get retreat. This is that kind of, hesitation before the ice started moving further north. While this is happening, we're forming glacial lakes, right? There's a lot of fresh water melting out of that ice. And if we have land around here, it's going to form a bowl, and that fresh water can form a lake. We know this by various sediments that form in freshwater versus saltwater. And here we are a little bit after 18,000 years ago. We're now forming Cape Cod Bay, and Cape Cod Bay was actually a lake, right? So we still had that kind of basin shape to it. It was just all fresh water because we had a huge, ice mass up here that didn't allow the fresh water to connect with the salt water on the other side. Kind of keep in mind this area here, the Pamet Valley, the Eastham Plains. There have been various kind of events where this lake is getting higher up than some of the surrounding sea levels, and fresh water is kind of draining through the Pamet Valley, a spring sapping valley, and then it can kind of catastrophically drain a large volume of material out of that lake. There we go. So we're talking about the Pamet Valley up here, kind of in Truro area. It was a spring sapping valley. It was a low area already. And then eventually when it intersected the lake, it can allow it to drain catastrophically. So you might think about like Ballston Beach, that kind of area. We get erosion and a reconnection every now and then. But this would have been a huge volume of water from Cape Cod Bay, which was a lake at the time, draining out into the ocean, kind of encouraging that low area as that flow really moved a lot of sediment at the time. Now, here's another look at the glacial lake, Cape Cod Bay, and that great south channel lobe. That's kind of the one that was a little bit east of Cape Cod. It formed various deposits, and you can think of it like a delta where you would have rivers coming down into this lake, getting some of that material that was up on dry land and distributing it out here. And so not only do we see freshwater lake material, we can also see small deltas. And this is, some of the building blocks of the Brewster Flat. Some of that material out there is all coming from this eroded material. It's not just the, lake beds getting reworked. It's really this coarser grained material that's forming our nice sandy beaches. It's not just, fine grained lake deposits and clay. So there's a lot of words on this particular slide. Don't feel that you have to read them all. This is in case somebody wants to look at it later during the recording. So we have some very high elevation features, and how did we get some of those? So this kind of bottom image over here, this is looking at the outer arm of Cape Cod, Eastham, Truro, those kind of areas where we had a lot of material deposited by those glaciers. Just think of, a very slow moving river of ice, but it's still moving and it was there for thousands of years. You're getting large volumes of sediment moving down, and it built up a large body of sediments. A lot of that sediment has eroded over time. It used to be much further to the east, but then, 6,000 years ago, we got a lot more erosive energy coming along the shoreline. And you can we're looking at a cross section. As this erodes, it moves to the north and to the south. So this is the material you formed Provincetown, formed Monomoy, sections of Chatham, places like that. So this is where we see some of our, lake sediments, whereas out here, this is all marine sediments. It's not just the fresh water from the glacier. A little bit further west over in the Buzzards Bay, kind of upper Cape Cod area, it was a different method of forming a moraine. It was called a thrust moraine. The heaviness of this ice actually had friction on the bottom, and it would kind of scoot this material forward over time, thrusting it forward and creating these ridges. That's one reason why that moraine has that kind of different configuration from some of the other moraines, the kind of classic terminal moraines that we see down on the islands. This is looking a little fuzzier than I like, but just another image of that kind of kettle and came topography. You can see these are kettle lakes, also known as kettle ponds. These are eskers. And all of these kind of formed in that glacial area. We're going to go through kind of one by one, taking a look at what they are, how they deposited, but just kind of keep in mind too, underneath all of this kind of superficial material, we're going to have till, which is unstratified sediment underneath everything, pretty much down to the bedrock. So here's where, we start getting some cool graphics that I found from other people. This is the drumlin up here in the upper left. So what's going on here, you can kind of, this is, the glacier, kind of a cross section of it, kind of looks like an ice cube, but think of it as a very large glacier. And this is what's happening where the ice intersects with the earth. And just looking at this again, it's kind of, thinking of ice as a river, right? You're still getting moving water. It's just moving slower because it's a solid at the time. But it's having bed forms. It's forming material down there. These drumlins kind of are egg shaped, and it's just kind of building up hills. And these hills can be pretty substantial because that ice can be up to a mile thick. So starting at the surface of the earth, looking straight up 1 mile of ice, tremendous amount of weight depresses the earth's crust, but also has a lot of, folding and mounding of material. So these drumlins are just kind of bumps that form on the Earth's surface. And after they glaciers melt away, those materials are still there. The Boston Harbor Islands are kind of classic drumlin features. That's why those islands have the elevation that they do. That's why they're out of the water, is because they had these large kind of egg-shaped mounds, and that's why we have the islands there. There's some other drumlin features up at Duxbury Beach, kind of the large bulbs on the end of some of those barrier beaches. And really, drumlins form a lot of the sources of sediment for these barrier beaches. There can be submerged drumlins that may be providing material to a beach. And when they kind of give all the sediment they could have given, your erosion really takes off after that because it's not getting the same sediment supply. So that's drumlins kind of in a nutshell. Over here is an esker. Now what's going on here, as the glacier is moving, it's not just solid ice. I mean, there's, some melt on the surface of the glacier. That water tends to infiltrate down through the glacier, gets all the way to the Earth's surface, forms tributaries, and eventually there's rivers underneath the glacier. That's what these eskers are. So under glacier rivers, you get deposits, typical river deposits. You'll have sand and gravel through here, and then you have the evidence of this, former riverbed after the glacier is melted. Moving on, a little bit cruder graphic, but one of the better ones I could find without me having to recreate it. This is called a came. What's happening with this is you have, pardon me, there we go. You have a large glacier, right? And there, for some reason, may be a hole in that glacier. So this is an area where there's not as much ice, a low spot. What's happening here is some of the surface water is going to flow in there. Some of the material, sediment, gravel, that sort of thing, is going to work its way into this hole in the ice. So then after all that ice melts, what's left behind is actually a raised spot, because the water goes away and you're left with the material that was in that hole. It's kind of like an upside down mound right there that you have that was created after the ice melts. And then the opposite side of that, we also talk about came and kettle. This is came, and so the opposite part is the kettle. So what's happening with this is you have chunks of ice that are left behind as the glacier is retreating, right? So each one of these large chunks of ice is left. It takes a long time, relatively, for it to melt. This material is still flowing out, covers up, some of the ice, around the ice, and then eventually, during warmer climates, the ice is able to melt. And then the cavity that was, filled with ice turns to water, forms these holes, these pits, and that called kettle ponds. Now, what's going on with this is, it's not just the melted ice that's the reason why these things have water in them. We have a very sandy soil that water would have infiltrated through and gone away by now. But what we have going, sorry, that keeps happening. What we have going on is an intersection with these low areas with our groundwater on Cape Cod. So if we didn't have a relatively high groundwater, these would just be low spots and eventually would fill in just due to surface runoff. But instead, we have groundwater flowing in, flowing in and filling up these ponds up to the level of the water table. And typically, the water is going to be flowing in one direction, usually towards the larger water body, pretty much always downhill. But it's headed out to Cape Cod Bay in the town of Brewster. So it's coming in here, it's filling up or maintaining the level of the Kettle Pond, and then it's leaving in this direction. This particular graphic or area of concern can happen when you're looking at where nutrients are coming from. If it's coming from the area immediately downdrift of the Kettle Pond, it may not contaminate the Kettle Pond as much. There may be more time of remediation through the soils before it reaches another water body. So when you're looking just at an aerial image of Brewster, there's certainly a lot of, very suspicious round water bodies all through this area. And these are the Kettle Pond areas, including that no bottom pond that I guess you guys have gone to on some of your Wednesday walks. Just a very classic example of an area where a huge chunk of ice used to be. And after it melted, this cavity was left behind and it's maintained by groundwater. A lot of times it may not be, perfectly round at the start, but after some wind and wave energy, not much wind and waves, these are very small water bodies, it tends to round it out over time. Moving away from kettle ponds, getting into glacial erratics.
Hey, Greg.
Oh yeah.
Can I interrupt you? I just had
absolutely
a question about the kettle and came. Do you know anything about the origin of those words? Are they related to one another, or is it?
Oh, I know. I'm not sure why it was called Kettle Pond. I'm sure there is a relatively good reason for it. Came has to do with another language, and I'd have to look it up. But no, not off the top of my head.
Okay.
So moving over on to glacial erratics. So what we're thinking of here are the really big stuff, right? So you may get cobbles, you may get boulders transported by glaciers, but these things are coming all the way down from Canada. They're going through Maine, coming through New Hampshire. Every once in a while, they get a chunk of mountain stuck in them, and it'll get transported the whole way. So when you're looking at a really big rock out there, and you're like, how the heck did this get here? Because just intuitively, this isn't something that got blown by the wind, and a wave didn't push this up from the ocean, a river didn't transport it with liquid water. The only way it could get here is supported by ice, and then as that glacier flows, it gets dropped out. So one of the nicest examples, the largest example from Cape Cod is Dome Rock. That's out in Eastham. And this is one where if you do go out and visit it, there's at least as much rock below the surface as above it. And it really, drives the point home that there's not many other rational methods for that huge rock to get there in a relatively sandy soil, right? So, I mean, you've got a lot of other outwash materials, but this is one that got placed there directly by the ice. Next feature to chat about is the flats, right? So here's another image that may, strike your memory from a previous talk, we talked about longshore sediment transport, how material kind of comes and goes from a certain area. Some areas are gaining, some areas are losing. And I mostly put this one up here because we can look about how the sand is moving along the shoreline itself. But obviously, there's a lot of material moving offshore as well. And that's one thing about the net sediment movement of this sediment budget that was put out, is that this is an average all the way across the flat and averages in the tiny ribbon of sand where we put, our towels and chairs at high tide. So as we move on, the Cape Cod Commission has a nice chronology viewer with some historic photos on there. As far back as 1890, and probably well before that, the flats have been out there. Very shallow water represented here. And then when we start getting aerial images, as early as the 50s in this case, we can see that the flats have pretty much always been there through, our recollections. We can advance to the 70s. And if you kind of keep your eye on some of the channels, it looks like maybe there is some movement out there, but it's hard to get a feel for how quickly things are going, moving into relatively new time. But really, since the advent of satellite images, that's when we can get a much more comprehensive view of how the flats move over time. So this was created using a Google Earth engine. And the idea is that it takes, the past 30 plus years of aerial images from satellite photos. So this is a satellite photo in each one of these images. And then it's, you can pretty much, if you go to the Cape Cod Cooperative Extension's website, we do have this on our coastal processes page, and you don't have to just stay in Brewster. You can kind of zoom anywhere and get this kind of time lapse of what's been going on. The main reason I put it here is you can really see the bed forms of the flats moving. So you can kind of get a feel for some of these channels moving from west to east, and some of these bed forms moving as well. And you can really see the erosion of the material on land here is directly feeding the flats as we go out. And when we're talking about, sediment transport, I've always got to bring up dunes, specifically the ones out in Provincetown. We talked a little bit about how erosion really started taking off 6,000 years ago. And that had to do with, Georges Bank finally not blocking, full Atlantic wave energy. So Provincetown wasn't there 6,000 years ago. And this image up here, this yellow, this is all a Holocene deposit, which means that actually wasn't put there by the glaciers. It's one of the few things that wasn't a glacial town. And there's Monomoy also is that same kind of yellow. And the idea is the orange is a floodplain or outwash plain from the glacier, but then that yellow is reworked material. So this is something that just happened in the last few thousand years, a relatively newcomer. Provincetown is kind of the wash ashore of Cape Cod. They're the recently arrived. And there's really no glacial material out there in Provincetown. Everything is a dune, everything is new. And when you start looking at some of this material, I mean, it's the same kind of sand, but just the shifting winds out there can really create some massive dune features. And it's not entirely natural. So when colonists, first got here, it was probably a fairly well vegetated forest system. And a lot of that material was cut down. And when it was cut down, that's what was stabilizing the sands underneath it. Once it went away, that material was able to move much more freely and created these large dune fields. So, it's got the potential to recolonize as forest eventually. But for now, we just have these, big, beautiful dune systems out here. that stay relatively sparsely vegetated just because of the volume of material moving around. So dunes and beaches are pretty much the what comprises a barrier beach, and I'm using Sandy Neck as kind of the classic barrier beach, but you guys definitely have barrier beaches here in Brewster. I'll show another example of that in a second. We're getting relatively close to the end of this presentation. So barrier beaches for Sandy Neck, there really wasn't much of a barrier beach 3,000 years ago, right? So it was just barely getting started. And then about 2,000 years ago, we had a relatively robust barrier system. And you could see right here, this time, we don't really have much marsh at all in this area. Now we're starting to get marsh development. And this is, relatively present time. We have a nice, healthy, extensive marsh in Barnstable Harbor. And that's really why they call it a barrier beach, right? I mean, it does protect houses from waves and flooding, but it's also this kind of quieter area. That's the only place a marsh is going to exist. You're just not going to get it out on the exposed sand area, and it takes a certain volume of sand to maintain a barrier beach, right? So it took a lot of erosion from Plymouth all the way down through Bourne and Sandwich, and this material has been moving from left to right, from west to east to create these barrier beaches. Tremendous volume of material pushing through here and pushing this along. And then, we're not really going to get into it too much in this talk, but interruptions to this flow of sediment, like the Cape Cod Canal, can really have an effect. It's probably having some effect out in Sandy Neck, but it's having a tremendous effect in the town of Sandwich area immediately downdrift. So this is one of the examples of, material is still moving west to east. It's just not coming from further west anymore. So it's depriving material. So you can think it doesn't just have to be a large jettied inlet that's interrupting the flow of sediment. It can be smaller inlets. It doesn't even have to be inlets and jetties. You can have revetments, seawalls, that sort of thing. Anything that can reduce the flow of sediment into the beach and dune system, right? So if you have a development with a seawall, it may be slowing down or preventing that upland area from eroding. But that's really the only way we get barrier beaches on Cape Cod. We need to, rework that glacial material in order to have beaches. We don't have large rivers up in mountains bringing material down like some of the other states to the south. We got, all our material, thousands of years ago when the glaciers were here. We're not getting much new stuff unless they truck it over the bridge. So this is how we're getting our beaches, is the reworking of it. So you can kind of look along this particular area, see if there's jetties, revetments, that sort of thing. And if you have a beach on the other side, it may be, kind of dwindling over time due to that reduction in sediment supply. And obviously, in periods of sea level rise, that's when we get erosional beaches. The faster the sea level rises, the more the erosion. But when you start, interrupting sediment supply, that's when you greatly accelerate the whole process. Okay, so this is
Greg,
pretty. Oh yeah, go
I'm
ahead.
just gonna have another question that's sort of relevant to what you're talking about right now.
Sure.
The sediment flow from west to east because of water flow or waves. What is the origin of the water flow? Is it wind, etc.? So why is that east to west? And I might as well just ask a question that I was thinking about when you were talking about because of the canal. Does the canal need to be dredged? Is the sediment, is that interruption causing sediment to go into the canal? So, but the first question was what's causing that flow?
Sure. Yeah. So a lot of this is covered in longshore sediment transport, right? So that's a talk that we covered a little bit last time, but also you can look on our websites and there's quite a bit of hopefully user-friendly information about how that works. The quick kind of, elevator speech about how it works is we're talking about parallel to shore transport. So it can also move perpendicular to shore, but for parallel to shore transport, uh, we're talking about wind energy as the main driver, right? So it's not the wind necessarily moving the sediment, but the wind moves the water, which forms waves. And in this example, along this stretch of shoreline, the average over the course of a year is that they tend to strike the shoreline and move material from west to east. So two main ways. I believe the question asked about flowing water too. So some of it is the direct waves striking the beach and dune, grabbing that material and pushing it down the beach as it erodes. But you can also get a current or flow of water moving along the shoreline in this case too. So not only do you have like material moving along the beach, but you can have a flow of water, which also transports sediment in that direction. So I can't really zoom in on this one, but this is one example where you have a long jetty on the west side of the canal here, and this is filled up over time. So you have many feet per year of accumulation in this area, and then you have many feet per year of erosion in this area. It just kind of stands to reason this is the winner, this is the loser in the overall sediment interruption game. So part of what's going on is this jetty theoretically should be long enough to capture most of the material and keep it there. What actually happens is some of it does get deflected and go around. Not very much of it, but the stuff that does often flows back into the canal. That's one of the reasons why the canal has to get dredged so often. Not that often, not as often as Sandwich would like, because that's where a lot of the sand on their beaches come from now. But in addition to that, we can get small scale reversals, right? So, I mean, material is moving from left to right in this image, but this jetty is pretty long. What that means is all the wind and waves are going to be blocked by that jetty. So more wind and waves are going to be pushing from right to left in the shadow of this jetty. So this area that's eroding is probably moving directly into the canal from that direction, which is one reason why a few decades ago they had to extend the southern jetty because of that reversal was pushing sand into the canal. So yeah, it's one of those, the more you mess with it, the more you have to mess with it. It's, but we do have flow of water going through. And I'm trying to think, was there another question or did I get them both with that one?
Yeah, you got it. We have some questions that I'll ask at the end.
Okay. Yeah, we're just another slide or so away and we can cover all the questions. So we're talking Barrier Beach. Here's probably one of the larger barrier beaches in the kind of Brewster area. We're looking here at Crosby Landing, and this is the barrier beach. Sorry, I didn't put an aerial on here. You'll have to take my word for it. This is a SLAM model, sea level rise, sea level affecting marsh migration, put out by NOAA. It's on their sea level rise viewer. So this is one where you can go to the online viewer and view this yourself. So this is, pretty close to now. It's like a half foot of sea level rise, not too much impact. These purple colors are marsh, low marsh and high marsh along the edge. And so when we increment forward in time or increment a higher water level using this, we're going to go relatively quickly. So here's 5 feet, right? So we've moved to 5 feet of increased water level. Oh, wait a minute. I jumped to 10. Sorry. So here's 5 feet of sea level. So you can see not as much purple along here. We're starting to see this light blue go in here. So this means it's wet all the time. It's not going to be that intertidal area where marsh can survive anymore. Some areas are getting a little bit more high marsh, but when you increment it again all the way up to 10 feet, you can see, barely any marsh. And this has a lot to do with the topography of the area, right? So this isn't, we'll often hear about marsh getting pinched out, and that's typically due to, human structures, whether it's bulkheads, seawalls, revetments, that sort of thing. When the marsh needs to migrate up against it, it goes away when it hits that point. Um, for this particular example, it's a little bit more insidious that um, if you think about a relatively gently sloping shoreline, there's more horizontal space for the vertical sea level rise. But for this example, it's relatively steep around here, which means there's not as much platform for that marsh to grow on. So unless the marsh can keep pace with the sea rise elevation, we're going to lose a lot of marsh just due to the overall topography of the area. And this is a model. Um, One of my favorite quotes about a model is all models are wrong, some models are useful. So what I like to take away from this particular example is it doesn't look at barrier beach migration, right? So I mean, this isn't just going to stay there and turn into marsh. It's going to, retreat. This is what these barrier beaches do. It's going to retreat and hopefully prevent some of this overwash area. In addition to that, some of these marshes may be able to keep pace with elevation. I know the National Park Service has been doing a lot of research into that. The USGS has been doing some studies on that as well. But that's really another talk. I just wanted to kind of whet your appetites about what has been going on. So this is, how marsh might migrate in the future, but marshes have been here for thousands of years too, right? So that peat underneath it has been part of that system that's allowed it to accumulate over time. And that is pretty much it for me. I think we can move over and take questions. And I think Dee, it's up to you. Should I stop sharing my screen or?
Yeah, I think you can stop sharing your screen. I'm looking at the, let's see. Didn't know if we needed to refer to anything, but you could share your screen if we need to go back to it. So reading the questions. If walking on any beach on Cape Cod, can you identify the origins of any rock found? There's such a variety of types of colors and beautiful different rocks. It would be nice to have a geologist to walk with and identify them all. Is that possible?
So I like to play that game. It's there's a tremendous amount of rocks out here. So I actually went to graduate school down in Florida, and we had probably two types of sand. It was almost all carbonate sand. Up here, we have everything that was dropped by a glacier. So we have everything from Canada, Maine, New Hampshire, and everything in between. Um, Sometimes I'll take a rock and I'll have to bring it back to the office. If I get really involved, I'll actually section it and take a look at it. But I mean, there's amazing sediment out here. Some of my favorite is you'll see some magnetite and that kind of stuff out in the cliffs of Wellfleet. And one of the ways you can tell that is if you take a plastic bag, get some material, and then bring a magnet back. You can, start pulling it out and seeing how it interacts differently. But it's, I'm not sure any geologist could tell you, walking the beach, what every rock is going to be, especially because, these are relatively weathered rocks. The easy stuff is the fresh rock when you can see the crystals and that kind of thing. But I mean, it is a wonderful potpourri out there of various types.
Cool. Question having to do with the kettle ponds. How deep are they?
Well, there's no bottom to that one, right? um, I don't know how deep everyone is. They can be surprisingly deep in some of them, but it really varies.
Yeah, and I will say for those of you that have been out to No Bottom Pond, that the theory is that if you're standing on Route 137 where the kiosk is and you're looking down to No Bottom Pond and you see the angle, it's a pretty steep hike down there. If you continued that line down and met on the other side, that's how deep it is. But nobody's ever dove down to see if that's true or not. It may have been that deep at one time. Let's see, can glacial erratics be traced to their original based on rock type, their origin?
I'm not sure if Dome Rock was, but yes, basically. So I mean, you can there is some, crystal analysis and looking at the specific makeup of some of these features. Like you can tell whether the granite is the same type of granite from up in the White Mountains, for example, that kind of thing. So you can, but again, this is one that you need to, break open a fresh face and do that kind of analysis. This isn't something you would do just walking around, but some of the studies have looked at where these some of the material has come from.
Okay. A couple more questions, 3 more questions. One, can you recommend a text for the introduction of Cape Cod geology?
Sure. So there's actually a few. I would look at Robert Odell. He has a good one, and they're going to kill me up at the Center for Coastal Studies because they just came out with a nice, well illustrated book about it as well. But yeah, the USGS and Robert Odell have a nice intro. And after that, I would check with the Center for Coastal Studies because I know they just put out one that was nicely done for kind of an intro into Cape Cod.
Okay. Can you comment on the distribution of clay deposits in Brewster? I know it holds moisture and doesn't drain well compared to the other sediments.
So sometimes I try to keep this close to what the question asked. So Brewster, like many parts of Mid-Cape, it's really hit or miss, right? So I mean, I could punch a hole, do a core, and find clay, and do another one, 20 feet away, and there's no clay. It's pretty amazing. But one of the issues that the person may be getting at is you'll get a layer of clay, right? And this layer of clay is relatively impermeable, so the water will infiltrate, go down, hit that clay layer, and then start moving, down. Water goes down, and so it's going to start moving, and eventually it may exit on the face of a cliff or a coastal bank versus continuing to infiltrate down and just eventually merging with the groundwater and saltwater lens. But when water gets its exit on the face of a bank, we often call them seeps. So when water seeps out of there, it can really erode a bank very quickly. So surface runoff isn't good. It's not for the stability of a bank. It's not good to have seeping water coming out the face of the bank. Some projects actually look at, punching holes in that clay layer to allow it to infiltrate to a deeper depth. So it may not, jeopardize whatever infrastructure, house, lighthouse, whatever you may have up there.
Okay, last question. There's what seems to be peat in some formations. When was that formed?
Let's see. So we came up with a paper looking at some of the peat swamps that were formed. I'm sorry, the cedar swamps that form the peat that get exposed out of Coast Guard Beach.
You just paused. We lost you for whatever reason. I don't know if you're paused for everybody, but you're paused for me.
barrier beaches
There you go.
and sandy shorelines started taking off in addition to the marshes of this area, it occurred because sea level rise slowed down to a pace at which these things could keep up. And I'm starting to get some internet instability, so hopefully that's not affecting too much.
Yeah, you went out for a little bit. Could you just answer that one more time?
Yeah, I'm sorry about that. So when we're talking about peat layers, um, again, check out our website. We got some, nice graphics and hopefully user-friendly information. We came up with one, what's that sticking out of the sand? Where you'll see peat layers, you'll see tree stumps, right? So you'll see tree stumps on the exposed, barrier beach, and that's not where they formed. They formed inland, but they start getting rolled over by the barrier beach, and now they're on the outer side. Quick answer, anywhere from ballparking 8 to 11,000 years, something like that. But it really depends on which marsh and which peat you're looking at. But a lot of them did form about the same time, and the same thing with barrier beaches. And that had to do with the sea level rise rate slowing down to a pace at which some of these features can maintain themselves, right? So if it goes too fast, the natural features can't maintain. But if it, keeps a relatively slow pace, we'll be able to enjoy them in the future.
Cool. Well, thank you so much, Greg. Someone's asking for the website, and I will send a follow-up email with a bunch of information, but you can just tell us the website real quick. And then also someone has looked up online that looks like quote unquote coastal landforms and processes at the Cape Cod National Seashore, end quote, at Center for Coastal Studies website store. So, but I'll send out a number of things, but you can tell us your website real quick.
Sure. So you can just go to Cape Cod Cooperative Extension.org. And then, you can also go to Woods Hole Sea Grant. But Cape Cod Cooperative Extension.org, and you go to coastal processes, and then, all our publications are on there, and just see what strikes your fancy. But everything is geared to taking, scientific information and translating it for applied coastal managers and for pretty much general consumption. So hopefully that will help. And if you're looking for something you can't find there, feel free to shoot me an email. I may know where it is.
Great. Thanks, Greg. Thanks for everybody joining. This is wonderful. We're really glad you're here. Have a good night, everybody.
Thanks for joining.
Bye, Greg.